So we're going to check whether this exercise is okay. This is the mechanical energy conservation equation, integral equation. So term A is 0 because nothing changes. That's stationary. That's right. Nothing changes with time. Term B, we have to compute the amount of energy flowing in and the amount of energy flowing out. So we assume that this is either horizontal, in a horizontal plane, or that the changes in height are neglectable. So we remove U, the potential energy. So we have in section A1, we have this minus B due to the normal vector. So we have this. This is positive, so this is okay. A2, A1. You have to use the continuity equation to get V2 because you don't know V2. You only know V1. So you will do this term. So eventually you get this, which seems to be okay. This is and then you have done this. You take one out. This seems to be okay. Then term C, you have at the entrance you have P1. You assume that you have P1 all over this surface A2. So this might be the no.
Nice.
We assume that we have P1 all over this surface A2. So let me see. So this must be. This is where.
There's something given at the.
Yeah, there.
Here. It's given.
Oh, you're telling you this.
The,
you can use this here. Time you pass row to the other side. Yeah. So, yes. Yeah. I'm not sure whether I am assuming P1 is over all the. Let's see. Where do you get this from? Actually, this is like too quick for me. I would have to do this. Okay, let me do this more slowly.
Okay.
See, I'm talking about C1, okay? Because you have C1 and then you have C2. Okay. Yeah. You have to C2. You haven't said anything about C2. I will tell you about C2. C1. C1. Which is this one, minus P times N times V ds, okay? This is C1. And then you have to do something like this. You assume that you have P1 over the whole A1, which is A2, sorry, this is A1, this is A2, so you will, and then you have the N, like this, you have V like this, you have V and N. So actually, due to this minus sign, you get the opposite signs as in term B. So in A1, you would write P1 times. This is negative, this cancels with this negative, so you have P1 times V1 times A2 actually.
Times A2?
Times A2 because you're assuming, let's see one second, let me write it like this. Let's just one second. Let's see whether this makes sense or not. Then you do have this minus sign because this is this is negative, this is positive, and this is so you have this one. P is P2 atmospheric or no? It doesn't. No, it's not atmospheric pressure, is it? No. P2 you have some P2. No, it's not atmospheric. No. So this is what you have here, minus P2 times V2 A2, but actually this is the volumetric flow. So
yeah,
you can. So if you add it up, you have delta P. Assuming delta P is P2 minus P1, you have delta p. Actually, this is equal minus delta p times any of them, because it's the same, any of them. Okay.
Yeah.
Is this what you wrote here? Yes, but yeah, you wrote this one. Yes. So actually, you know, delta p is the opposite of this. The thing is, you didn't say why C2 was 0. That's what I'm going to show you now, that C2 is 0 everywhere, okay? C2, you have this term tau times n times v. You have this, okay? So on the walls, v is assumed to be 0 on the walls. Let's see, we have A1, A2, and then we have like walls. Okay? A1 and A2, we assume uniform velocity. So, you know, uniform velocity means the velocity doesn't change with the space.
The gradient is 0.
So the gradient is 0, so it's tau prima, tau dot, comma, whatever, is 0. So everything is 0 here. And SW, the problem is we assume the velocity on the wall is 0. So here you get another 0. And D, it's incompressible, so this is 0. And then E is the thing we want to compute. We want to calculate this. Okay, so this is what we are looking for. So maybe, I'm not sure where the mistake is, but it seems to be okay. Are you getting something really different? Is it just a matter of some massage?
This one.
Is it completely different, or?
Yeah, because I have another term here.
But you have to substitute this delta p with this. You cannot leave delta p like this. You have to use this expression here. So I guess once you put this into play here, you will get dv, because everything you have done is perfect. Okay, can you try to do that?
Yeah, try first.
Yeah, because it's.
I think I did it at home, but
Oh.
I didn't get it. So that's why I asked
My
you.
suggestion, well, it might be a matter of some massaging the you know,
But
some
but
algebra.
if I
some
leave the
algebra.
question like the answer finally like this,
It's better to use delta p, because delta p is actually
it is given here.
it's given, so you have to use delta p. Leaving in the exam this something like this wouldn't be okay.
Okay.
It would be almost good, but not 100%. Okay.
Okay. All right.
Is it clear for you, this one?
Yeah, I think so.
Yeah.
But
No, if you
one
want,
question first.
we can elaborate a bit more if you
Yeah.
need more.
This is we got here
Yeah.
square right here.
Yeah.
But at here, how can this one, if we substitute here, we can get this square.
Square anywhere.
But
Yeah.
this one, we cannot just
I
simplify this
understand it.
one.
My suggestion, it can be a matter of massaging the equation, some algebra. So what I would suggest, if you input this into Wolfram Alpha, for example, you input your solution, you subtract it from my solution. If it gets 0, then it's the same, but with different, you know, some algebra.
All right.
So
Okay.
sometimes this can be written in different ways. Okay. Just try it at home. Don't worry too much about this, because
But so far that I did it.
this is, I mean, the procedure is perfect.
Okay. All right.
Okay.
Just I need to elaborate here more.
Yeah.
The term
Yeah.
C1
Maybe you
and
need to
C2.
elaborate. Maybe you need some algebra here or somewhere.
Okay.
Okay. Good.
So far it's okay. Okay.